lesson on section 9.4 series. And in this section, this part of the video, we're going to talk about infinite series. So let's start with the definition of an infinite series. So an infinite series is an expression of the form. So we're going to have our summation, and now we're going to use n as our index, n equals 1, and now on top we're going to have infinity of a sub n. So what this is telling us is we're going to sum the terms, but there's no last term because it's an infinite series. It's going to keep going on and on. Even after you get to an nth term, you're still going to go on even more. So one thing we do is we look at partial sums. So what a partial sum is, it's the sum of the first n terms of an infinite series. So that'll help us determine some of the behavior of an infinite series. So how do you find the sum? You do it in this manner. So we have our summation, and we're going to start at k equals 1 to infinity of a sub k. And what we can do is we can take the limit as n approaches infinity of so many terms, n terms. So we'll change the upper index from infinity to n. So now we're just looking at partial part of the series. And what we want is for that to come out to be some number. So what we can say is if S exists, then the series converges. So it doesn't just keep getting bigger, 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 or smaller, smaller, smaller. The numbers are actually heading towards one specific value. And that's a good thing, because then it does have a sum that we can say, like it's 15 or -1 or something. Otherwise, the series diverges. And has no sum. Okay, so that's what we're going to work with. The idea that hopefully our series will converge and will have a sum. So let's see that in an example. So this is number 23 on page 664. So we're supposed to find the first 6 partial sums. So there's two parts to this. So part A, here's what we're given as our series. So we have 0.3, then we have 0.03, then we have 0.003, and then we have 0.0003, and so on. Okay, so our first 6 partial sums are just going to be adding these terms together. So S1 will just be the first term, because you're adding one term, and then S2 will be to add the first two together. So you have 0.33. S3 will be to add the first three together. So you have 0.333. And so on. So the fourth term will be 0.3333. S4 will be 0.3333. 2, 3, 4. Oh, this is S5, sorry. I'm saying to myself, I feel like I already wrote this one. And then S6 will just be 6 threes. Now, the idea behind this is, we're going to see this as we go on, that this is how we find out that a repeating decimal is a rational number. Because, as you can see, we can write a repeating decimal as a infinite series. So we'll get to that in a minute. So part B then is 1 minus 2 plus 3 minus 4 plus 5 minus 6. So our first 6 partial sums will be 1 for the first term, and the second will be 1 minus 2, which is negative 1. And then the third partial sum, we'll take our second sum and add 3, so we get 2. And then our next partial sum, we're going to take our 2 and subtract 4, so we get negative 2. And then our fifth partial sum is going to be negative 2 plus 5, which is 3. And then our sixth partial sum is going to be 3 minus 6, which is negative 3. And what I'm going to note here is this series diverges. And how I can see that is bounces back between negative and positive. So it's never going to settle towards one number. Whereas part A, you can see it's heading towards a certain value. Okay, so how do we talk about convergence of geometric series? So let's start with a theorem. Theorem of the sum of an infinite geometric series. Now these are really nice to work with because there's a real nice formula for it. So the geometric series so we have the summation k equals 1 to infinity of a times r to the k minus 1. And if we want to say that a cannot equal 0, that's our first term, converges if and only if the absolute value of r is less than 1. Now r can be a negative number, but we're looking at the absolute value of that. So if it converges, the sum is this nice little formula, S equals A times 1 minus R. You can see it's a little familiar from our formula in the last part where we had a finite sum, and we had A times 1 minus R to the n over 1 minus R. So when you're talking about an infinite sum, you take the limit. This is what it simplifies to. And this is a very useful formula. Okay, so let's do an example here. Page 664, number 25. We are to determine whether the infinite geometric series converges. And if it does, find its sum. So here is the series. So we have 6 plus 3 plus 3/2 plus 3/4 is what we're given. And then, of course, it continues like that. So the first thing you have to do is determine your R. So we have to figure out how this goes from one term to the next. And hopefully you can see that we're dividing by 2. 6 divided by 2 is 3. 3 divided by 2 is 3/2, or 1.5. So our R is going to be 1/2. And since R equals 1/2, the absolute value of R is less than 1. So this converges. So now we can find our sum. A is going to be the first term. And then we're going to do 1 minus 1/2. So we have 6 over 1/2, which is 12. So if we were to add up all the terms, it would add up to 12. Okay, and then finally, we're going to finish our discussion with how we can use a geometric series to write a rational number as a fraction. And it comes from the fact of what we did in number 23 earlier. So that's how these two things are connected, which is, I think, kind of cool. So we're supposed to express the rational number as a fraction of integers. And so here's our number, 7.141414, etc. So we're repeating decimal. So I can write this out as a series to make it look like we did in number 23 above. So I have the 7, and then I'm going to add to it each of my repeating parts. So I have a 0.14 plus, and I'll have 2 zeros there for that first 14, and then the next one, and then I'll write one more out just like it's in that picture, and then I'll have another set of zeros for the second set of 14, and so on. And what I can see is every time to go from this part to the next part is I'm multiplying by how many points I have there, which is 1/100, or 0.01. So that's my R. Okay, so my A is going to be, we're going to ignore this for now. Our A is just going to be the 0.14. We're just looking at the decimals. And the R then is 0.01. So I can use the formula for a sum of an infinite geometric series, because that's what this is, which is A over 1 minus R. So that's going to be 0.14 over 1 minus R, which is 0.01. And so this is going to give me 0.14 over 0.99. And I can ignore those, so I can divide by 100. So I get 14 over 99. And then all I have to do is add 7 to it. So I have 7 plus 14 over 99. Now we want it as a fraction, so I'll have to change 7 to a common denominator. And that comes out to be 693 over 99 plus 14 over 99. And that's going to equal 707 over 99. And you can check that in your calculator, and you will get this decimal. Okay, if you have any questions, please feel free to let me know, and I'll be glad to help you.